Boldly going where no science show has gone before. The Naked Scientists.
On this week's Naked Scientists, how doctors have found a way to cure the rates or reduce the rates of stillbirth by over 25% in some countries. Also, a revolutionary new way to monitor cancer patients to give them an early warning in case their cancer shows signs of coming back. And how a plant that can survive near total desiccation for years on end and then come back to life as soon as it gets wet again could hold the key to producing stable vaccines that don't need refrigerators. Great news for third world countries. Hello, I'm Chris Smith, and also here this week to help us with the show is Dr. Kat. Hello, Kat.
Hello, Chris. Thank you. Also coming up this week, we're looking at new ways to extract energy from the wind. It doesn't involve eating baked beans, but the wind that's in the sky. We're going to be hearing how scientists have used the design of a whale's fin to make breakthroughs in turbine design, a new kind of wind-powered generator that flies like a kite to get up into the jet stream. Plus, we'll hear how South African researchers working down in the Antarctic have cut their research base's dependence on diesel. Fantastic stuff.
Thank you very much, Kat. And if you're feeling experimental, then this week's Kitchen Science should appeal to you. Ben and Dave will be exploring what happens to a bottle of hot food colouring which has been immersed in a bowl of cold water. The answer is on the way. In the meantime, if you would like to get in touch with us, you can email chris@thenakedscientist.com or send us a tweet on Twitter. It's @NakedScientists.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, I'm going to start our news this week with a story that shows that life-saving research doesn't have to involve complicated or expensive technology. It sometimes just needs a little thought and application, according to new research in this week's New England Journal of Medicine. Now, researchers funded by the US National Institutes of Health and the Bill and Melinda Gates Foundation have discovered that a short training course can help cut the rate of stillbirths by more than 30% in the developing world. Now, given that estimates suggest that there are 3 million stillbirths worldwide each year, and nearly 4 million infants die within a month of their birth, that's a staggering difference for such a simple solution.
What actually have they done, Kat?
Well, the researchers were testing the effectiveness of a 3-day training course for birth attendants or untrained midwives, which highlighted simple techniques for caring for newborns, things like breastfeeding as well, keeping babies warm and dry, and looking for signs of serious health problems.
But why has this been overlooked in the past?
Well, this is the thing, is that there's a problem with delivering this kind of training. There's a lot of midwives in the developing world, so you have to actually try and get training out to them. Now, they did this by sending one healthcare worker from Argentina, the Democratic Republic of Congo, Guatemala, India, Pakistan and Zambia. They went over to the US to learn these special newborn care techniques, and then they went home to train other midwives and healthcare workers in their area, and they reached around 3,500 healthcare workers in rural communities. Now, the researchers also taught the healthcare workers how to check infant health to diagnose whether a baby was stillborn or whether it could be made to breathe, and to check for other conditions. And they also provided them with scales for weighing infants, for handheld pumps and masks to help fill babies' lungs with air, and also clean delivery kits to help prevent infection at birth. And then, obviously, they wanted to test if it worked, so the scientists compared data on babies born before and then after the training had been given.
Impressive numbers that they got to. What did they actually find when they did the analysis? Did it work?
Well, overall, they studied 120,000 births, and they found that the rate of stillbirths dropped sharply. So there was around, before the intervention, there was around 23 stillbirths per 1,000 deliveries, and that dropped down to just under 16. Now, the scientists think this is because some of the babies wouldn't have taken a breath on their own when they were born and would have been considered to be stillborn, but actually the birth attendants could recognise this and help the babies to start breathing with some very simple techniques, and actually in many cases save its life. Now, supporting this idea, the researchers didn't find a difference in the number of babies who actually appeared to have died in the womb before they even got to birth, suggesting that actually it is recognising when babies just haven't started breathing on their own and intervening at the right time. And it's a very simple intervention, but giving the right training to the right people and spreading it out in this way, it really can help to save lives.
Indeed, and certainly impressive numbers. Big reduction, so that's certainly something which we should bear in mind as a sign of how simple things can make a big difference. Now, sticking with things that could make a big difference, something that was only just unveiled this week at the AAAS meeting in San Diego, that's the American Association for the Advancement of Science, is a new discovery which could enable us to tackle one of the arguably most malignant aspects of having cancer, which is that the disease spreads. We're very good at treating primary cancers, so when a tumour starts somewhere, surgery and other interventions like radiotherapy are very good at dealing with the local initial disease. Very often you can cure that aspect of it. But usually by the time someone presents to a doctor, the tumour has already spread to other parts of the body. This is a process called metastasis. Keeping tabs on whether that has already happened, whether the therapies that patients are given have actually been effective, and then following people up to see whether their tumour is recurring is actually very much a black box. It's very difficult. There are very few ways of doing that until now, because there's a study by Rebecca Leary, who's a researcher at Johns Hopkins in America. What she and her colleagues have unveiled is a new genetic technique that enables them to study the structure genetically of cancer cells and produce a genetic signature so that they can track a cancer through a person's body by just taking blood samples.
So is this looking at DNA in the bloodstream from the tumour cells? How do you tell what's wrong with the tumour cell just from this DNA?
You're right, it is looking in the bloodstream because cancer cells very often break down and die and they splurge out the DNA that they normally have in them into blood. The blood then goes round in the bloodstream and can be detected using genetic techniques. Cancer is a genetic disorder, and what characterises cancer cells is that the genetic material in a cancer cell is very unstable. So very frequently, whole bits of chromosomes will break off of their normal chromosome and stick themselves onto another chromosome. And this puts segments of DNA next to other segments of DNA that they would never normally be next to. And what these researchers have done is to work out a way of very rapidly genomically sequencing through a tumour, so they have the entire genetic repertoire of a tumour, and they can see where these funny translocations, these movements of bits of DNA, have gone from one place to another, and this gives a unique fingerprint for the particular cancer. The next step is to then just keep taking blood samples from the patient after they've had each of their interventions and see how the levels of DNA from the tumour in the bloodstream fall. If the levels fall to 0, that shows that probably all the cancer has been removed. If it doesn't, it argues that there's still some traces of that original cancer in the bloodstream somewhere, and that argues you should do more therapy.
Well, it sounds absolutely fantastic, because obviously it's a non-invasive way of monitoring whether a cancer's there or has gone. But isn't it going to be phenomenally expensive? Genomic sequencing is still pretty costly.
Indeed, it cost the Human Genome Project about £500 million and about 10 to 15 years of effort to try to sequence a human genome. But technology since that time, 10 years ago or so, has moved on enormously quickly. And people are in a position now where they can do a complete human genome sequence for about $10,000 to $20,000, which means it's only about 4 or 5 times the price of doing a CT scan, which is the current gold standard way of diagnosing cancer and diagnosing cancer in a recurrent state. In other words, has it come back? And the point is that a CT scan has a limit of sensitivity. You've got to have a lesion or some kind of tumour which is visible to a scanner. When you're doing DNA technology, you just need a molecule of DNA to make it detectable. So this is very, very ultra-sensitive, but it is a research tool at this stage. It's only been validated using laboratory samples of colon cancers and breast cancers in patients. And it's going to be another, obviously, few years yet before people begin to work out how to integrate this into the clinic.
Exciting progress, though. And another kind of technology that's still in its infancy, but again very simple compared to Chris's more complicated genome sequencing, is one for our crafty listeners. Now, I don't know, Chris, are you into craft? Maybe your wife likes a bit of sewing, knitting, that kind of thing?
Actually, I can knit, but not very well. And that's only because I was bored once and I got my gran to show me. She's brilliant.
I'm a big knitter, and if any of our crafty listeners are fond of whipping up a skirt or a shirt or something like that, the cotton thread that you're using could actually be used to make a lab on a chip. According to new research from scientists in Australia, they've used cotton thread and simple sewing needles to stitch together a lab on a chip that could one day be used for cheap diagnostic tests for medicine or other applications. And they've published their work this week in the journal Applied Materials and Interfaces.
But chips normally involve things like silicon and metal, don't they? So how can you use something like thread for this?
Well, these kind of chips are called microfluidic devices, and they pull tiny amounts of liquid around their surface in a tightly controlled way. And you're right, they're normally made by etching channels into silicon or glass or metal, some kind of hard surface to make chips about the size of a postage stamp. But the scientist called Wei Shen and his team, they figured out they could actually make a microfluidic chip just using cotton threads to wick liquid around surfaces instead.
And how do they actually do this? How do they test it works?
I love this stuff. This is great. The first challenge was to actually prepare the cotton thread. Now, natural cotton fibres are actually coated with wax, the natural wax from the plant. So first they had to use a special treatment called plasma treatment to strip the wax off. And then they stitched this treated cotton thread into paper in different patterns to make little microfluidic sensors that they could use to detect and measure different chemicals that, for example, are found in the urine of patients with certain illnesses.
And how does that work?
Well, they were testing, in this case, for nitrite ions and uric acid, both of which can be detected by chemicals that change colour. So they took some paper and they treated it with these detection chemicals before sewing the cotton thread into them. And then, when you dip the end of the thread in urine or a solution of these ions, then it changes colour. It wicks the solution around the paper and changes colour. So effectively, you're making a paper and thread-based detection lab.
Very nice. What's next for doing this? Are they actually going to try and wheel this out in the clinic?
Well, this is, at the moment, very experimental. It's a fairly crude demonstration of the technique. But maybe with a bit more research, a bit more application, it could be possible to develop some very cheap and effective sensors for many different chemicals. They're simple, they're cheap to make, relatively unskilled people could make them. So it would be ideal for applications in the developing world. You could sense contaminants in drinking water or soil, or use them for very simple diagnostics for healthcare applications. So you could have tests out in the clinic, in the field, that might be able to help diagnose illnesses.
Which is another very important story. Thank you for that, Kat. Now, something else that caught my eye this week, which was really quite surprising, is that for a long time scientists have understood that cells work by having genes in them, and those genes can be turned on or turned off to make various chemicals in the cell, and those chemicals in the cell then do various jobs that contributes to the cell's metabolism. We understood that. But in more recent years, scientists have also found that genes have the equivalent of a dimmer switch. This is epigenetics. By adding chemical groups to the sides of various bits of DNA, you can affect how active individual genes are. Well, scientists pretty much thought that was it. But now a group of researchers have shown that there's another, third dimension, if you like, of control of a cell's metabolism, which is that the proteins that those genes make can themselves be controlled in terms of their activity. There's a paper in Science this week. It's by Ximin Zhao and colleagues at Fudan University in Shanghai. And what they show is that the proteins in the cell that function as enzymes and do various important metabolic jobs, what can happen is that wherever there are lysine groups, one of the amino acid building blocks that make those proteins, the cell can add an acetyl group, a chain of 2 carbon atoms, onto those lysines, and this affects the behaviour of the protein. It can make the protein more or less active. So this gives the cell a whole different new way of controlling how active some of the metabolic processes are in the cell. And to do some simple experiments, what they did in liver cells was to incubate those cells in different amounts of glucose and demonstrate that in that changed environment, the amount of acetyl groups being added to these lysine residues changed dramatically, and alongside that, the level of activity of the enzymes changed dramatically. So this gives cells a whole new way to get programmed metabolically.
So that's really fascinating that this is a whole new pathway, but do you think it could have applications in therapies, in sort of maybe metabolic disorders, how we can treat those?
It may well do, yeah, because most of the time we're looking at drugs that will basically affect the way in which cells behave as a fairly blunt instrument. But it might be that by controlling this process, as well as trying to control the activity of various genes and things, because some of the new drugs coming up for disorders like diabetes, for example, actually control the activity of whole clusters of genes in cells. It might be this is a new way of controlling the activity of various components in cells that are linked to disease processes, and it means we could make even better drugs that are more bespoke to certain conditions with fewer side effects. So certainly very interesting, and something that people had previously completely overlooked.
And it just sounds like it's making life more complicated when we're trying to understand how cells work.
Thank you, Kat. Well, more exciting news now, because also this week scientists have announced that they've discovered a way to use a secret known previously only to nature to solve a big problem in the third world, which is how do you keep viruses, and particularly live viruses that you're going to use as vaccines, alive despite a lack of refrigeration. Well, the secret has come from a plant called the resurrection plant, which is an incredible organism. It can withstand near total desiccation. You can dry it out for months on end, in some cases years, and then it springs back to life as soon as it touches water. I know this because I've played with it myself. Scientists have discovered how that plant does that, and they've now been able to borrow the same trick and apply it to viruses. And Matt Cottingham joins us from the University of Oxford. Let's start with the plant first. How does it do this?
Well, the key is that it has lots of trehalose inside its cells. And trehalose is a common sugar, which is similar to sucrose, which is ordinary table sugar. And when the sugar dries out, it forms a glass. And a glass is a particular type of chemical entity, which is essentially a liquid that's so viscous that it's effectively a solid. And actually the glass in your window is called glass because that's the type of chemical. And although it seems completely solid, it's actually chemically a liquid because the molecules are disordered.
So it stabilises, presumably, the cells and the components of those cells in the plant so that when the plant dries out, the chemicals and the structures don't fall apart. So when you do add water, the sugar then breaks down again and everything comes back to life.
That's right. If you take all the water out of something, what would normally happen is you get crystals. And crystals have a very tight structure, and they will actually disrupt the structure of the plant, or in this case the vaccine, which you want to preserve. So by having lots of sugar, which doesn't crystallize under those conditions, but instead forms a glass, that actually allows protection against desiccation.
So how have you stolen what the plant's doing and applied this to the vaccine technology world?
Well, it's very simple. We simply take a mixture of sucrose and trehalose and formulate the vaccine into that, and then dry it. And what we've hit upon is a particular method of drying that actually enables the vaccine to retain its structure and its activity.
Which viruses are you thinking of? Because obviously there are certain viruses that are pretty stable and you don't need to do special tricks to make sure that people can get infected with them. I'm thinking of common things like norovirus, which people catch on cruise liners. Not all viruses are as stable as that, though.
That's right. So most viruses are quite stable, but they really need to remain wet. So they're normally transmitted in droplets, say from a sneeze, or via the fecal-oral route, where you've probably got a tiny bit of moisture on your fingers. But in this case, if we want to be able to stabilize these, it's really crucial to have them dry, because if they're dry, then the chemistry which would normally degrade them can't actually happen.
So which viruses are you looking to use, and how?
So we've focused in this work on two viruses, adenovirus and a pox virus called modified vaccinia virus. And these are exciting because they're two viruses which may be used to form the platform for a new generation of vaccines against diseases like malaria and HIV and TB, where there aren't any vaccines or where the current vaccines are no good.
And what is the impediment or problem with using these agents in the third world at the moment?
Well, the problem is that they're live viruses, so they're living organisms, and they're very sensitive to heat. So all the live viral vaccines at the moment have to be kept in the fridge. So they're usually manufactured in Europe, and then they're shipped all over the world in refrigerated containers, and they then have to be kept in the fridge at the destination. And if they do warm up, then they essentially have to be thrown away.
I would presume then that the actual spend on keeping vaccines cold probably makes up a significant proportion of the total cost of the vaccine then?
Yeah, it's about 20%, and that doesn't include wastage.
Which is a huge amount and obviously totally beyond the realms of many countries to spend money or even to have the infrastructure to keep a vaccine cold. So presumably your platform would enable you to put viruses into these sugar glasses. They would therefore be stable at what sorts of temperatures for how long?
We've managed 45 degrees for 6 months.
Which is pretty impressive.
Yeah, it's amazing.
You presumably then would just take the vaccines out to the bush in the middle of nowhere and they would remain stable until someone had them administered.
That's right, yeah.
Do you think that these sugars would be safe in
they're
the body?
Completely safe.
How do we know that?
They are actually already used in the current vaccines, some of the current vaccines. So it's a combination of these sugars together with the new method of actually performing the drying that has enabled us to do what we've done.
Any idea when you'll be able to wheel this out and when people will begin to see the benefit of this?
Yeah, we're thinking possibly as early as 5 years, maybe more like 10, because we've done this very much on a laboratory scale. So now we have to actually do it according to good clinical manufacturing practice, which is a set of legislations which we need to adhere to in order to make a product that can actually be used in humans. And that's being done by our commercial partners, Nova Laboratories in Leicester.
All right, well, we wish you luck with it, and thank you very much for joining us, Matt, and telling us about your work. That was Matt Cottingham. He's at the University of Oxford, and he and his colleagues have published a paper. It's in Science Translational Medicine this week, in which they outline how these new sugar-based glasses can be used to make viruses survive intact in very otherwise hostile conditions.
Keeping you abreast of the world's best science, The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Kat Arney. If you'd like to contact us through Twitter, it's @NakedScientists, or you can send an email. It's chris@thenakedscientist.com. Kat.
Now, when you see a whale, it probably doesn't make you think of wind turbines, but our next guest, the very aptly named Professor Frank Fish from Westchester University in the States, was inspired by the fins of a humpback whale to design a better wind turbine. So we're joined by Frank. Hello.
Hi, how you doing?
Hi, good. Now, tell us about the story behind this, because I understand that you saw a picture of a whale and it set off your train of thought.
Actually, it wasn't a picture. It was a little bit more three-dimensional than that. It was a sculpture of a humpback whale. And I saw that it had, aside from very long flippers, these very curious bumps along the leading edge, the front edge of the flipper. And I was quite embarrassed because I actually started just saying that this was impossible until I did see a picture, and then tried to figure out why it had these curious bumps that you just don't see on anything else.
It does seem counterintuitive. You'd think that bumps would interfere with the action of the fin. So what are the bumps doing?
Well, what it appears is that they modify the flow. So if you have a wing-like structure, like taking your hand and putting it out a car window and then playing airplane, what will happen is a wing will modify the flow of air. It'll push it down, and as a result, you get a lift force as you raise the angle of the wing. And that occurs up to a particular point, in which case the hand or the wing will go through what's called a stall if the angle's too big, because the air flow or water flow can't move around it in a nice controlled fashion. So stall is something you don't want to happen. It's awful when it happens in airplanes. But for the humpback whale, what the bumps do is that they can increase the angle at which you can have that flipper directed into the flow without stalling.
So you can have a sharper angle and get more drive from the wind?
Exactly. So the whole idea is that because you can raise it at a higher angle, what's called an angle of attack, you can then place it into a wind or water flow, and you can get more lift out of it, and thus more energy if you're putting it into a windmill. And you can also have a safety factor. So a big problem with windmills is that you get gusts of wind from any direction, and that sometimes exceeds the stall angle. And the result is that the windmill becomes unstable. It starts to vibrate and can even sort of blow apart. With this, you can actually have a higher angle, get more energy out of the wind, and in the same way also protect the windmill because it's less likely to form these vibrations.
So how have you been applying these kind of bumpy fins to wind turbines? Have you got large-scale ones, or is this kind of just small-scale work at the moment?
Well, I work with a company, and we've had a test windmill up in Canada, and it was about a 30-kilowatt windmill, test windmill, and what we found is that under moderate air speeds, we could actually get a 20% increase in the amount of energy that we could produce with the windmill.
That sounds absolutely phenomenal. Why have people not thought of making bumpy wind turbines before?
Well, again, it's sort of counterintuitive. I mean, whenever you see wing-like structures, we always think that they need a nice, sharp, clean leading edge. So airplanes or car spoilers or windmills or fans, anything like that. So this is a bit counterintuitive that you wouldn't think of putting these bumps along the leading edge. And part of the argument has been that if you do that, you're going to disrupt the flow in another way, and that is you're going to increase the amount of resistance that wing will go through the air or through the water with. And what we found with the bumps is actually there is no penalty for having these bumps along the leading edge. They don't increase the resistance. And additionally, as you go up to higher and higher angles, there's actually a reduction in the amount of resistance compared to a wing that doesn't have the bumps, simply because the wing isn't stalling. When it stalls, the amount of resistance goes up quite a bit. So we can operate at higher angles with less resistance than if we didn't have the bumps.
That sounds brilliant. We've had a question in from Second Life who says, is this similar from the dimples on golf balls? Is it a similar function that's going on?
It sort of has similarities, but there are distinct differences. What a golf ball does by having the dimples on it is it turbulizes the air over the surface of the golf ball. So normally air will move in sort of nice, even layers over a surface, and that's what we call laminar flow. The trouble with laminar flow is it's not very stable. You can't maintain it at very high speeds or with very large entities. And so by having the dimples, it turbulizes the flow over the golf ball, which means that the flow will continue over more of the surface, and as a result, there's less resistance, and the ball travels further when it's hit. With the tubercles, or these bumps along the leading edge, what they do is they do create a different flow regime, but not necessarily turbulizing the flow. What they do is they produce large swirling masses of flow, what are called vortices. And these vortices interact over parts of the wing to actually help to speed up the flow over, say, the bump itself, and keep that flow attached over the entire surface of the wing so that, again, you don't stall out.
So at the moment you're testing this wind turbine up in Canada, do you think, how long might it be until this starts to be adopted more widely as turbine technology?
Well, I think it's ready to go. The big problem is that there's always a large capital investment in redesigning structures such as windmill turbine blades, especially when you're talking about very large wind turbines. We have had success in actually putting these on ventilation fans. And there again, we're seeing that there's a improvement for the manufacturer because they can push as much or more air with fewer blades by having the bumps on the fan blades. And so what that means for the producer is that there's less material costs, and then the actual fan operates with greater efficiency, which means for the end user, they're going to pay less in their electric bills to ventilate some area using the fans with the bumps.
Well, fantastic. That sounds like a great example of stealing from nature to make something that's greatly improved. So thank you very much, Frank. That's Professor Frank Fish from Westchester University explaining how the bumps on the edge of a whale's fins have inspired him to make new, better wind turbines. Chris?
Nat Spirit got in touch from Second Life Cat, where Second Lifers are listening to the programme. Hello to all of you. And he says he's picturing, having heard that item, a whale spinning round rapidly on the end of a pole. Very funny. What a wonderful example of nominative determinism, though, Frank Fish. And, of course, fish are not whales. Please don't anyone tell me about fish not forms of Wales. Wales is a country, of course. I've got a question here from Dennis Sloan, who says, why is it colder at higher altitudes? I was told once that since you are going closer to the sun as you go up in the altitude, it'll get hotter. Therefore, as you're close to the sun, it's hotter. Why isn't it warmer at higher altitudes? Why is it colder? Well, the reason, Dennis, is if you think about it, the distance between the Earth and the Sun is a very long way. It's 100 million miles or so. And therefore, the distance between the Earth's surface and, say, the top of Everest at 29,000 feet is a fraction of the total distance to the Sun. So it's a trivial change in the actual distance. So that isn't why the temperature changes, and it isn't, therefore, much hotter. The reason it's actually colder is because as you go up in the atmosphere, the Earth's atmosphere feels less pressure the higher up you go. And as gas rises and feels less pressure, this will make it expand. When the gas expands, it does some work. And if it's doing work, it must be losing some energy. And if it loses energy, its temperature must drop, because we define temperature as the average energy of the particles. And therefore, if the energy in the particles is lower, the temperature must be lower. And that's why at altitude the temperature appears to fall. In space, outside the Earth's atmosphere, if you're facing the sun, you can actually fry. And that's why spacesuits are well designed, especially designed in order to keep people from getting too hot in the sunny bits and too cold in the cold bits.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Dr. Chris Smith and Dr. Kat Arney. We're talking about the power of the winds this week and how we can get energy out of it better. Also on the way is our question of the week, in which we find out whether shovelling up snow from roads, roofs and pathways actually could contribute to global warming because we're not putting as much sunlight back into space. What do you think the answer is? If you'd like to get in touch with us, Kat's going to tell you how.
If you want to get in touch with us through Twitter, it's @NakedScientists, and you can send an email to chris@thenakedscientist.com.
Thank you, Kat. Now, how do you power a research station in Antarctica? Well, the answer is usually with very large diesel generators. And that means you also need to get the diesel down there, and that costs a lot, both financially and also from an environmental perspective, because you've got to burn more fuel to ship it there. But now scientists from the South African National Antarctic Programme, they're SANAP for short, have come up with a much more environmentally friendly solution, which is they're also making use of the notoriously powerful Antarctic winds. And Mira Senthilingam caught up with the Antarctic's temporary resident, Johan Stander, who's a mechanical engineer at the University of Stellenbosch.
Most Antarctic stations are quite dependable on fossil fuels and will becoming more expensive to fuel stations. Not only the fuel itself, but transporting the fuel to Antarctica. And then secondly, governed by the Montreal Protocol, we are actually obliged to minimize the environmental footprints of stations in Antarctica. That's why we actually investigated the feasibility of sustainable energy sources of solar and especially wind, since Antarctica is one of the windiest places on Earth. We designed turbines specifically to harness the Antarctic wind, which is quite extreme compared to other wind sites in the world.
And how did you set about designing this turbine for this particular environment?
First of all, the most important obstacle is the low temperatures in which the turbine should function. In that case, we spent some time selecting specific materials that can cope with in the low temperatures, varying from plus 10 degrees Celsius to minus 40 degrees Celsius in the winter. So the steel, we select steel that has a high carbon content. We select the epoxy for the blades that is also used in aircraft design. And we kept the turbine itself as simple as possible, robust as possible design, meaning less parts, more reliability.
And what about things like oils for, say, movements of the turbine blade?
So the only thing we're actually using as a lubricant is grease, and the grease is a synthetic grease, and it's food lubrication grease, meaning it's also biodegradable to some extent. It can cope with temperatures up to minus 50.
And how many of these turbines have you made so far?
So far, we're testing a prototype. That is a 15 kilowatt machine. It has a hub height of 12 meters, a rotor diameter of 7.2 meters. The blade itself, it's a black blade. Okay, it's a glass fiber epoxy blade, and then a shell, which is the actually interface between the rotor, the tower, and the tail vane. It's a steel structure. We didn't go for an active yawing system, the yawing system being the system that keeps the rotor in the wind. We went for a passive system just to eliminate the amount of parts needed and obviously make maintenance easier. And the tower itself is a lattice structure, which obviously have less effect on snow accumulation or induce less snow accumulation than tubular tower. And foundation, it's a rock anchor foundation. Since we are limited in construction materials and construction time, that was the easier option.
Just how windy is Antarctica? So what kind of wind speeds do you get there? And are they quite predictable wind speeds? Are they constant or are they variable?
Compared to other wind regimes in the world, Antarctica is known for its katabatic wind regime, which is actually driven by cold air. It's like opening a fridge and when you feel the cold air rushing over your feet. That's the same principle, the same mechanism that's actually governing Antarctic winds. The wind is quite extreme. At the highest wind speed we've measured here at Sanai in the last 7 years was 62 meters per second at a height of 10 meters. temperature-wise, the colder it gets, the more extreme the wind. At the moment today, the wind speed is around about 7 meters per second, and the maximum temperature is -2. What is quite interesting when comparing an Arctic wind regime to a normal wind regime is that it's quite constant throughout the year. At Sunday, it's around about 11 and 9 meters per second for at least 60 to 70% of the time per year.
So what's the expected figures for the amount of power it's hoped to produce then?
So far, we have converted about 100 kilowatt hours during the test, and the capacity factor of the machine or the site is 80%, meaning it will operate at rated power for 80% of the time per year. The wind energy that will be converted is estimated at equivalent to 30,000 liters of diesel fuel.
So how would the turbine work? Will it be running constantly, and therefore will it be actually creating power that can then be stored?
There's no storage at the moment. Since it is such a small system compared to the diesel generator system we have, all power will be fed to the station, and in days of excess wind, where the power is not required, it will be dumped in the snow smelter, which actually provides the station with water. So there's no storage, all power will be fed to the grid.
So in terms of the prototype, it seems to be working very successfully. So if this continues, will you be scaling this up in the future for the site?
After the end of this year, we will increase the amount of turbines. So we'll erect 2 more turbines, then increase the total capacity to 45 kilowatts. And then maybe in the future, we can, if the foundation does allow, we can change the generator, increase the capacity of the generator.
And I guess that makes sense because a lot of the work actually taking place out in Antarctica is looking at the environment and the effects of things like climate change. So it makes sense to make the site itself as efficient as possible and therefore not contributing to this in itself.
It's saving diesel fuel and reducing emissions, increasing the autonomy of the base. That's the main aims. I mean, what's the point of doing research here while polluting?
Absolutely. That was Johan Stander from the University of Stellenbosch, who has now returned to slightly warmer Cape Town from Antarctica, and he was talking to Mira Senthilingam there. And just in case you're wondering how fast an average wind speed of around 9 to 11 metres per second is, that's about 25 miles an hour. That's a force 6 or a strong wind on the Beaufort scale. Definitely what you'd call a wind chill factor.
Thank you very much, Kat. It's Chris Smith and Kat Arney with you, and we're talking all about the science of the power of the wind and how we get energy from it. Coming up, how scientists have discovered a way to get energy from the jet stream by flying a wind turbine up there. That's on the way.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists. It's Chris Smith and Kat Arney, and we're talking about the power of the wind.
If you want to contact us through Twitter, it's @NakedScientists, and you can send an email to Chris at chris@thenakedscientist.com.
Thank you very much, Kat. Now, capturing the wind at ground level is pretty effective, but not everyone is as lucky as those souls down in Antarctica with those horrendously strong and very cold winds. Winds are much higher, though, up there, higher up in the atmosphere. But how do you get a wind turbine up there to make the use of them? Well, Pierre Rivard is a researcher who works for Magen Power, and they're a company who've developed an inflatable answer to the problem. Hello, Pierre.
Hello, good to be here.
Welcome to The Naked Scientist. Please tell us, first of all, how much more powerful are the winds that you can get access to if you can get a bit further up there?
Well, Chris, the wind power is a cubic function of speed, meaning by that if you double the wind speed, you have 8 times the wind power available to you. And in most locations around the world, going as high as 1,000 feet above ground would double the wind speed accessible to wind power.
So in other words, you could turn your average wind turbine from pumping out, for a big one, 500 kilowatt probably, into, something at least a megawatt?
Yes, but more importantly, the percentage of nameplate capacity that would be gainfully employed could as much as double. In other words, a typical wind turbine would be productive only at 20% of its nameplate capacity, but up there it could be employed to as much as 50% of its nameplate capacity, which reduces the stranded asset element of wind power.
And this is what you're saying with respect to the fact that the wind up there, higher up, blows regularly, reliably, and most of the time, whereas down on Earth, unfortunately, it doesn't.
Yes, absolutely. Professor Ken Caldera from Stanford University with his colleague Dr. Christina Archer characterized this energy as the most concentrated source of global renewable energy on Earth. They believe that there's enough energy up there to power the needs of civilization 100 times over, and it's only a matter of time before we learn ways to harness this energy.
Speaking of which, you've got one possible solution. Talk us through it.
Okay, well, we've demonstrated what we believe to be the world's first airborne wind turbine. We were followed for a year by Discovery Channel in 2007 and demonstrated 1 kilowatt of airborne production of electricity, and we brought it down through a tether to ground level. We're now engaged in scaling up this 1 kilowatt prototype to 30 kilowatts, which we hope to achieve by mid-year this year, and rapidly scale up to the 100 kilowatt mark shortly thereafter. Okay,
so the basic premise is that you have a system that gets a generator way up there, high in the atmosphere, 1,000 feet or something?
Yes, we're starting at 1,000 feet because the length of the tether is less daunting in terms of lifting its own weight. Our design is very unique. We use a kind of a paddle wheel kind of wind turbine, which we elevate to 1,000 feet. And again, because we have 8 times the power accessible to us than what we would have at ground level, the actual energy conversion efficiency is not quite as important as the fact that we have 8 times the power available to us as what we would have at the ground level.
So this looks like a giant suspended water wheel, I guess is one way of thinking about it, isn't it? So you float that up using something buoyant, helium presumably, to get it up there.
That's correct. We could use other buoyant gases such as hydrogen or natural gas, or some of the welding gases, but we use helium right now because it's an inert gas and it's the best way to start. Ultimately, we could use hydrogen, which could be renewably produced using water and electrolysis in the developing world.
So this takes the generating system up to 1,000 feet or so, where it sees the wind, and this causes it to rotate. So presumably you have a core spindle which is stationary, and the body of the generator rotates around that spindle, and that's how you get the power out.
Yes, that's correct. We have some proprietary ways of doing this. Some of the aerodynamic challenges, which were documented in the Discovery Channel program, identify that there's a challenge in flying a paddle wheel broadwise to the wind, but we managed to solve this issue. And we've also moved away from a central generator on the axle to a more innovative approach, which we find is to be lighter and would also leverage some automotive parts from the electric car industry to reduce costs, but also to enhance the commercialization of the product.
And you recover the electricity down the line that's supporting or tethering the machine up in the air?
Yes, the tethering is very important. We use a plastic by the name of Vectran. For some of the listeners, they may know Vectran as a plastic that has more strength than steel on a per-weight basis. And within the Vectran tether, we have some embedded copper wires that would bring down the electricity to the ground level. And we also have some data links within the tether. So it's a highly engineered tether at the present time, and this is no longer a technological issue for us.
Presumably you could use this where you wanted sustainable, reliable power, but in, say, remote places. So if you were running a station in the middle of a desert or something, rather than have to lug loads of diesel out there to have a generator, you could put one of your systems up in the air above where you're working and just bring the power down to the plant.
Yes, indeed, Chris. This is one of the typical crucial applications. Our tagline is wind power anywhere. And really, when you think about the 1.6 billion people without electricity on Earth, when you use, let's say, solar, you have a renewable source that is intermittent, and without storage, it's difficult to harness around the clock. However, our device, because the winds are more constant and stronger at altitude, multiplies the number of sites where wind becomes economical and makes sense, and certainly to bring renewable energy to the rural electrification of China and India, we believe we have a great solution here.
And just to finish off, the one thing that's going to occur to many people is, I hope there's no airports nearby.
Yes, we have to abide by some regulations. If we are within a certain radius of an airport, we obviously would not get a permit to fly. We need to provide some light markers every 50 feet along the tether, and we also need to, our device also has a transponder on board the device, which means if it becomes, in the unlikely event that it becomes unattached, then a local radar could track it as it travels because of the transponder on board. So everything is done according to regulations, and it hasn't been an issue in the demonstrations we've done to date.
Brilliant. Well, we must leave it there, Pierre, but thank you for joining us. That was Pierre Rivard, who works for Magen Power, based over in their Canadian company, but also right across America. And as long as you live in an area where there are no aeroplanes, then they could have the solution for you in the form of a way of generating power using an inflatable turbine. Kat.
Fantastic stuff. Let's go fly a kite and generate some power. Now it's time to join Ben Valsler at Dave Ansell's house for a colourful kitchen science.
For this week's Kitchen Science, Dave has thoroughly confused me. He's invited me into his kitchen to do an experiment that shows where the wind comes from, and yet the thing he's got set up is a large bowl full of water. Now, Dave, I think you might have got it a bit mixed up. We're talking about wind, about air, not about water.
Well, air is a fluid, it flows. Water's also another fluid that flows, but water's a much sort of denser fluid. It means all the experiments happen a lot slower, so it's easy to see what's going on.
So we're sort of using our bowl of water as a metaphor for the wind.
As a metaphor for the atmosphere, that's right.
OK, so what do we have to do?
Well, first of all, you want a nice big bowl of water.
Warm water, hot water, cold water?
Just cold water. Then you want a little bit of food colouring and a very small bottle. Ideally a small, fat glass one, but I've only got a short, thin plastic one. It'll have to do.
And you're actually using a food colouring bottle, but you don't want to use a full bottle of food colouring.
You just want sort of 2 or 3 drops of food colouring in the bottom of your bottle. Gently pour that in.
Now, obviously, if you're doing anything with food colouring at home, be careful because it can stain. That's what it's supposed to do. So don't get it on your clothes, and certainly don't get it on anyone else's clothes. OK, we have a few drops of food colouring in the bottom of a small bottle. What's next?
I want to fill this up with hot water from the tap. Just let it run for a bit so you get some nice hot water out of the tap.
OK, so it needs to be quite steamy hot, but not dangerously hot.
Just filling this right to the top.
Oh, you really mean right to the top, don't you? There is no air left in that bottle at all.
Yeah, that's the idea. I'm just going to hold the lid on upside down so it just holds it in there and keeps everything stable while I put it into the bowl of water.
OK, so we're not actually screwing the lid back on, we're just placing it on the top, and we're going to put the entire bottle into the large bowl of cold water. So in we go.
I'll take the lid away.
So that's completely submerged in the large pot of water, and you've actually knocked it over. Did you do that on purpose?
Well, it turned out my bottle was too tall, so I just have to knock it onto its side.
OK, so you've taken the lid off now, and the hot food colouring stained water is streaming out of the bottle. It almost looks like if you turned the whole thing upside down, it would just be pouring out, but it's actually pouring up.
Yeah, that's exactly what's happening. When you heat up water, all the molecules vibrate more, they take up a bit more space. So the water becomes less dense, which means it will float on the water around it.
So a bit like oil will float on water because it's less dense than water, the hot water in your coloured bottle is doing the same thing, and it's pouring upwards to settle on the top of the water. But there are a few very interesting tendril sort of mushroom shapes coming back down from the red liquid where it's collected at the top.
That's right, it's floating upwards, then it gets to the top and it cools down again. Eventually it gets cool enough that it will sink back down again. So we've got warm water rising at the end of the bottle and falling in other areas of the bowl.
It's actually beautiful. It's almost making little ringlets of coloured water as it falls back down to the bottom. I wish you'd chosen a colour other than red, because it almost looks blood-stained, but it's a very, very pretty effect, and clearly it's demonstrating what I think is just convection.
Yep, this is convection. Warm fluids tend to expand and float, and cool fluids, as we can show now, tend to sink. So what I've got here is some ice cubes I've made with a load of food colouring, so they're really, really dark blue.
It looks to me like your ice cube tray might be permanently ruined.
Yes, don't tell my housemates.
Well, as long as you make them fancy blue cocktails, I think you'll get away with it.
OK, now I'm going to try floating one of these on the surface of the bowl.
Now, ice, of course, is less dense than water, so the ice itself will float on the surface. And as I'm watching now, it's starting to melt, and the blue food colouring is coming out. And again, we're getting these tendrils of colour coming down through the bowl of water and heading towards the bottom. So exactly the opposite thing is happening. Will they eventually warm up and pull back up to the surface?
If there was a heat source at the bottom of the bowl, especially if it goes and sits near that hot bottle, it will warm up and then start floating up, and you get a circulation with movements of water.
OK, so this is a beautiful and colourful and really simple demonstration of how convection works. But what's it got to do with wind?
Well, it's actually the force which drives wind and most of our weather. The sun beats down on some parts of the world better than others, so some parts of the world get very, very hot. The air above them also gets hot. That means it's less dense than air in cold places. That means the air from the cold places will kind of fall under them and the hot air will float upwards. So you get lots of movement of air around the place. You get winds.
So the hot bits are where you get thermals, where you'll see, say, birds of prey or even people with a glider. They are riding on these hot columns of air that are moving upwards as the cold air around them moves inwards and pushes them up.
Yes, and the really extreme version of this is a hurricane. But that's got the slightly added complication that the Earth is spinning, so that as the air moves in towards the centre, it spins faster and faster, like if you ever played on a children's playground on a roundabout. So you climb into the middle, the roundabout spins faster. So the air spins faster and faster and faster until the winds get absolutely devastating.
So this colourful, watery demonstration actually demonstrates the physics behind some of the extremely destructive forces of nature. That's all we have for Kitchen Science this week, and we'll be back with more very soon.
So food colouring and water can show you how a hurricane works. Absolutely fantastic. We've got pictures and video of Dave destroying bits of kitchenware and the multicoloured action resulting from it online at www.thenakedscientist.com/kitchenscience.
Frank Fish, who's still with us, we got a question from Silverwing Benoit, and if you can do this very, very briefly for us, Frank, he says, could we use your whale dimple technique on aeroplane wings as well?
Sure. The quick answer is yes. What it allows us to do is to make the wing and the airplane safer because you can operate at higher angles and really go beyond where a plane wing would normally stall. As a result, then, you don't need all of the mechanics and extra control surfaces that you find on airplane wings. You can eliminate those and all the heavy components that go with it. That makes it more economical for a plane to fly because now you've lightened the plane, makes it easier to get off the ground and to fly along. And this way, you can either make it cheaper to fly or you could actually take your wing and add more fuel in there, and the result being that you can extend the range of the plane. You won't have to make as many stops. So this is potentially beneficial to airplanes as much as windmills or any other lifting surface.
Thank you very much for doing it so quickly. Now, this is The Naked Scientist with Chris and Kat, and it's a very special day today because it was this very day, 10 years ago, that the first ever edition of the show that ultimately became The Naked Scientist actually got broadcast. And it all started in the first place because a group of us at Cambridge University ended up on a local radio station during what was called National Science Week. This is back in 1999. This gave us a relationship with that radio station, so we then ended up eventually with a radio programme that we launched there 10 years ago today in the year 2000. So, you can imagine quite how horrified I was when I replaced my car earlier this year and, clearing it out, discovered in the glove compartment a cassette that said on it 1999. And when I played it, that was that first programme from 1999's National Science Week. So I have a little bit of it for you, and for a bonus mark, perhaps you can tell us who this interviewer you're going to hear on here is, or where else you've heard him.
Turn to you, Chris, to discuss the differences between the sexes and, brains.
Well, of course, it's a very evocative subject, the difference in sizes of brains, things like that. But and it will probably displease a lot of women to know that actually men have a larger brain than they do.
Yes.
The average size of the men's brain is, on average, 1.3 litres. That's 1,300 centimetres cubed. And
so
in
that's
women,
a regulation size 5.
Well, it's the average. I mean, we're talking the average here. and in women it's about 1,200 cc's. So men have a larger brain than women do. So
football for a man, ping-pong ball for a woman?
Well, I wouldn't go that far, but it's not far off.
Not far off.
Quite close, isn't it?
We do actually have some ladies in the studio here. They're going to be talking about some other bits
they don't look happy, actually.
No.
I'll stay on this side.
I used to sail very close to the wind, but we did go on to say after that women do actually appear to use their brains a bit more efficiently than men do, which might account for some of the differences. Now, those women that were referred to as being there in the studio with us, one of them you might recognise.
Yes, let me introduce to you this evening Kat and Harriet. Thank you ever so much for coming along. Have you had a good week with Science Week and everything like that?
Yeah, I never want to see another kiwi fruit ever again, though.
Yeah, what's this about kiwi fruit then? What have you been doing?
Last Saturday we were in the zoology department.
Right.
We got hundreds of kiwis, and we extracted DNA from them.
DNA from a kiwi?
Mm-hmm.
Yep.
How on earth?
Kiwi fruit, is it?
Yes.
Yeah, not the New Zealand variety. No.
Green
green fruit type.
So, without being this might sound like a ridiculous question, but how do you go about doing something as complicated as that? I mean, is it very complicated to...
Well, it's not complicated so long as you have washing up liquid and salt and a saucepan.
No.
Yep. You boil up your kiwi fruit with washing up liquid and salt. And strain it. I think we strained it into champagne flutes, because we do like high life at Cambridge.
Coffee filters, we strain it through.
Yeah.
Right.
And pour in some meths, and there you go. Kiwi fruit DNA will form in the middle.
Well,
That's
I never.
DNA appearing before your very eyes.
Is that just with fruit that technique works?
It tends to work with fruit because fruit give out their DNA very easily without too much contamination generally from the rest of the fruit. But probably if you mashed up bits of human, it would do that. But I think that's
probably
maybe
left
not the right
alone
experiment.
at the moment.
The radio debut of Dr. Chris and Dr. Kat. The mystery voice was, incidentally, Pete Cousins, and he still appears on The Naked Scientist every single week, although you may not realise it. He is the guy who makes all our fabulous jingles for us. So there you go, Kat, that was you and me. In the same studio, but didn't actually talk to each other very much, just over 10 and a half years ago when we did that.
It's incredible, yeah. It's a real blast from the past. I think I said some absolutely idiotic things. And, yes, I think I probably sound a bit less posh and definitely less squeaky and more professional now, I should hope.
Indeed. Well, hopefully we all do. I don't know how I ever managed to carry on in radio. I would have given myself the sack if I'd been the person running that programme 10 years ago. But there we are. I wanted to say, though, that because it is 10 years of this whole thing this year, we are going to have a little party later this year. And if you would like to come along, we will be announcing details of where this meeting will be and what we're going to do for it to celebrate 10 years of The Naked Scientists and the project in general. And it will be later in the summer this year in the UK. So watch this space. We will be coming back to 10 years of The Naked Scientists shortly.
And I hope there will be cake. Anyway, now it's time to hear from a consummate professional. It's time for our question of the week with Diana O'Carroll.
This week, how snow might keep the whole world cool.
Hi, Naked Scientist. This is Jacob Kemmerer from Virginia, USA. I'm currently snowed in right now, and I know that painting rooftops white would help cool cities. I was wondering if plowing snow would cause any global warming or add any additional heat to the Earth.
So, does ploughing snow from the roads have a measurable effect?
I'm John King, and I work at the British Antarctic Survey in Cambridge. Well, the thing about snow is that it's quite reflective compared to bare ground. A good thick snow cover will reflect back up to 80% or even more of the sunlight that's falling on it, whereas bare ground or grassland might only reflect 10 or 20% of the sunlight falling on it, and so the sunlight warms it up considerably. So if you replace that bare ground by snow cover, then a lot of the sunlight that would have heated the ground just gets reflected back into space. So if you remove a snow cover by ploughing it up or sweeping it away or whatever, revealing the bare ground underneath, then the ground is going to absorb a lot more sunlight and will warm up a lot more quickly than if the snow were there. We are having an effect on the reflectivity, the albedo of the planet by changing land use, for instance, cutting down forests and replacing them with grasslands, but that generally has the opposite effect, that forests absorb quite a lot of sunlight, grassland is less reflective. People have suggested that we could partially offset global warming by painting the roofs of all of our buildings white. And I think some calculations have been done that have showed that maybe this would be a good thing, but it wouldn't have a very large effect because you're only talking about a rather small area of the planet that you'll be changing the reflectivity of.
Human action does have a measurable effect on the albedo, that's the reflectivity of the Earth's surface, but only on the huge scale of farming. So ploughing snow, even from long motorways or highways, probably won't make much of a difference globally, but it might make a difference locally. And on the forum, Diver John pointed out the insulating properties of snow, which, as long as it stays on the roof, can help to keep the heat in your house and therefore reduce the energy you have to put in to keeping your home warm. And from a pale reflective dilemma to a see-through one.
This is John Gamble from Louisville, Kentucky, and I've had a burning question in the back of my mind when I went to a scientific meeting of ocular scientists down in Sarasota, Florida. There was this lovely young scientist from Budapest who forgot her bathing suit and put on shorts and a white T-shirt when she went swimming, and she was alarmed, and some of us not so alarmed, to discover that the T-shirt became virtually transparent as soon as it got wet. But she realized this, and she also was smart enough to hold the T-shirt away from her body. When she did that, it was no longer transparent, and I'm not really sure what the optics involved and why that happens. I'd be very interested if someone could offer an answer.
And I bet every man there was very gentlemanly, yeah. What is it that makes clothes become transparent when they get wet? Answers on our forum at thenakedscientist.com/forum. Or email chris@thenakedscientist.com and we might just read out your answers on our question of the week.
So, why do white clothes become transparent when you get them wet? Anyone been entering a wet T-shirt competition lately? Do let us know by email to chris@thenakedscientist.com or scribble it down on our forum at www.thenakedscientist.com/forum.
Thank you very much, Kat. And as if wet T-shirts weren't enough watery science, we'll be back next week looking at how building a dam can change the local weather, how to find out if you're losing water from your pipes, and how a changing climate will actually impact on water security worldwide. If you have any questions on any of those issues, then you can send them to us. It's chris@thenakedscientist.com. You can write them on our Facebook page, Naked Scientists, or you can tweet at us. It's @NakedScientists. Meanwhile, I have to say a very big thank you to our guests this week, who are Matt Cottingham, Frank Fish, Johan Stander and Pierre Rivard, and also our wonderful production team, Mira Senthalingam, Diana O'Carroll, Dave Ansell, Ben Valsler and Tom Simpkins. Thanks also to Dr. Kat. Do join us next week if you can, and until then, goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.